In this video, we're going to talk about the derivative of the natural logarithmic function. If we let u be a differentiable function of x, then the derivative with respect to x of the natural log of x is equal to 1 over x if x is greater than 0. So let's think back to the second fundamental theorem of calculus. If we know that the natural log of x is equal to the integral from 1 to x of 1 over t dt, then the derivative with respect to x of the natural log of x would have to be equal to 1 over x. So that's just what the second fundamental theorem of calculus tells us. So that's all we're saying here. Now, if you happen to have the derivative with respect to x of the natural log of u, notice that the x and the u don't match here. That just means you'd have to use the chain rule. So that's going to end up being 1 over u times the derivative of u with respect to x. Now, to shorthand this, we usually refer to that as u prime over u. So you'll hear me say that a bunch throughout this chapter. That's a u prime over u. So, for example, if I wanted to find the derivative with respect to x of the natural log of 5x, I would let u be equal to 5x, so that means that u prime is going to be 5. So this is the derivative with respect to x of the natural log of u, which is u prime over u, which is 5 over 5x, which is 1 over x if you cancel the 5's. So that is my derivative. In this case, I've got the derivative with respect to x of the natural log of u, where u is 3x squared. So u prime would be 3 times 2x, or 6x. So this is also u prime over u, which is 6x over 3x squared. I can cancel the 6 and the 3 to leave a 2 and a 1, and I can cancel one of the x's. So I actually get 2 over x as my derivative. For this example, I would have u equals 12x, so u prime would be 12. So the u prime over u here would be 12 over 12x, which is going to be 1 over x. So you'll notice if you have k times x, it doesn't matter what k is, you're still going to get 1 over x as your derivative. This example is interesting because in order to be able to do this problem, we have to use the product rule. That we would need the product rule because we have x times the natural log of x. So I'm going to let my first function f be x, which means that f prime is 1. And I'm going to let my second function g be the natural log of x, and the derivative of the natural log of x is 1 over x, so that's my g prime. So this is going to be fg prime plus gf prime, which is x times 1 over x plus the natural log of x times 1. And notice my x's cancel, and I end up with 1 plus the natural log of x. This one you may think you have a product rule because you have a natural log and you have a square root. But the thing about this is the natural log doesn't have a meaning unless you plug something into it. So you really want to think of this as the natural log of the square root of x plus 1. And there's actually 2 different ways that you could go about this. So I'm going to show you both of them. The first option, you could go ahead and let u be equal to the square root of x plus 1, which is x plus 1 to the 1/2. And then using the chain rule, u prime would be 1/2 times x plus 1 to the negative 1/2 times the derivative of the inside, which is 1, or 1 over 2 square root of x plus 1. So coming back to the original problem, this would be the derivative with respect to x of the natural log of u, which is u prime over u, which is 1 over 2 square root of x plus 1, divided by the square root of x plus 1. Or if you do the whole keep, change, flip thing, I would multiply by 1 over the square root of x plus 1. And when you multiply a square root times a square root and you've got the same input into both of them, it just becomes x plus 1. So I get my answer as 1 over 2x plus 2. So that's one option. The other thing that you can do with a problem like this is you can use the properties of a natural log to your benefit. So I could make this the derivative with respect to x of natural log of x plus 1 to the 1/2 power, And then I could use the power rule and bring the 1/2 out front. So this is the derivative with respect to x of 1/2 times the natural log of x plus 1. I could bring the 1/2 out and make this the derivative with respect to x of the natural log of u. And in this case, my u would just need to be x plus 1, which means u prime is 1, the derivative of x. So this is 1/2 times u prime over u, which is 1/2 times 1 over x plus 1, or 1 over 2x plus 2. And it's up to you which one you think is easier. I actually think it's a little bit easier if we don't have to deal with the chain rule inside of this whole messy thing. So, or at least not as hard of a chain rule. So you can see how the properties of logarithms can actually make your life a lot easier. Show you another one of these where using the logarithmic properties can actually make the work go a lot quicker, or at least be a lot more simple. This one's the natural log of this kind of big messy fraction here. I've got x squared plus 2 to the 5th power divided by x cubed minus 7 to the 12th power. So I'm going to start by breaking this apart using the quotient rule. So this will be, or the quotient rule for natural logs, not the quotient rule for derivatives. This will be x squared plus 2 to the 5th minus the natural log of x cubed minus 7 to the 12th. And then I can make it even easier by bringing these out as a multiplication. So this will be the derivative with respect to x of 5 times the natural log of x squared plus 2 minus 12 times the natural log of x cubed minus 7. And then I can split this into two derivatives, and I'm actually going to go ahead and bring the constants out for each of them. So this is the derivative with respect to x of the natural log of x squared plus 2. And this is going to be minus 12 times the derivative with respect to x of the natural log of x cubed minus 7. So on the left here, I would have u equals x squared plus 2, so u prime would be 2x. So I'll have 5 times 2x over x squared plus 2. And then on the other side, I would have u equals x cubed minus 7, so u prime would be 3x squared. So this would be 12 times 3x squared over x cubed minus 7. And just to go one step further with it, I have 10x squared, divided by x squared plus 2 minus 36x squared divided by x cubed minus 7. Now you can go ahead and find a common denominator for that, but it's not absolutely necessary. Now think about this. If you had not used the logarithm rules to your advantage, this would have been really messy, because your u would have been this whole thing right here, and then you would have had to have found the derivative of that using the quotient rule for derivatives and the chain rule twice with two different change of variables. So it could get really messy really fast, whereas using the logarithm properties, this was pretty straightforward. So let's take a look at one more type of special property. Now another thing that's really handy with the natural log and the derivative of the natural log is that if u is a differentiable function of x such that u is not equal to 0, then the derivative with respect to x of the natural log of the absolute value of u is also equal to u prime over u. So if I want to take the derivative with respect to x of a natural log of an absolute value, it's really not any different than taking the derivative of a natural log of any other u. So in this case, this would be written as the derivative with respect to x of the natural log of the absolute value of u, where u is equal to cosine of x, and we know that the derivative of cosine is negative sine of x. So this is going to be u prime over u, which is negative sine of x over cosine of x, and it happens to be that sine over cosine is tangent. So this is negative tangent of x.